So just before we start, I just want to tell you something. So if anyone having trouble with the classes, attending the classes, or doing the homeworks because of COVID or any of the current situation, please directly message me. Okay, it should not be a problem. We'll work out something. I'm just again telling you this. Specifically, the students, if any of you are facing any problems in the family or anything because of health or any issues, you just immediately let me know. Okay. Okay. So today we will start the DMRS. Let me just open up the spec. So until last class, we were looking at MIMO. At least I hope that we had a decent introduction of MIMO. So today what we'll look at is we will start looking at the reference signals. Let me just open 38211. Okay. So it's a downlink thing. So we finished layer mapping, we finished all those things. And then we don't require virtual this thing. So now the first thing is the reference channel. In this, we will do the demodulation reference signal for PDSCH. Okay. So remember, PDSCH is the main data channel for the downlink. Okay. So one thing that you should remember, at least in 5G NR, which is specific to 5G NR, is the reference signal DMRS. This is called DMRS reference signal. DMRS reference signal for PDSCH will be there only in the resource blocks that are allocated to the PDSCH. Okay, what I mean by that is, so this is your resource grid. Okay, and if a particular user is allocated only these resource, this is the resource elements that are allocated. Okay, then the DMRS for that particular user will be there only in this grid. The other users will have their own other DMRS. Okay, so each DMRS is very specific to the PDSCH for that particular user. Okay, it's tied in very well. Okay, it's a port. It's like a port. Okay, so we will see that. Oh, just remember that the DMRS is specifically tied to that particular user. Okay, so how is the DMRS generated? So the DMRS is a pseudo-random sequence. The bit it's a QPSK signal. If you see, this is a QPSK signal. It's 1 by square root 2 times plus or this can be plus or minus 1. C of n is a binary sequence, 0 or 1 sequence. So if C of n is 0, then you get 1. The highlighted one will become 1. Or if it is 1, it becomes minus 1. Okay. So R of n is a QPSK signal. Okay. So all the reference signals are generally QPSK in 5G NR. Okay, and how is the pseudo-random sequence generated? We have already seen this once. The pseudo-random sequence is generated this way. Okay, so all you require to know is to generate this pseudo-random sequence. You require something called a seed value. Once you know the seed value, you can this is a gold sequence. You can generate the pseudo-random sequence. Okay. Is this fine?
Yes, sir.
Okay. So if you look at this init value, this is interesting. This init value. Okay. So what does this init value depend on? One is L. L is the OFDM symbol in which you are going to put this. What do you say? This reference signal. That is one. This L. Okay. I just want to see if I can find a point. I can't find it. You can see my cursor, na? Okay. Okay. NSF is the slot number, and NID, SCID. There's some way in which they generate this SCIDs. NID 0 and NID 1. There's so in general, what is NSCID is N cell ID. Okay. Otherwise, if there's some other way of generating this NSCID, they give this thing. I will not worry about that too much. So effectively, one thing that you should remember is the C in it is something that changes as per your which slot number you are in and which symbol number you are in. Okay, so once C read changes, the C sequence changes, and once the C sequence changes, R of n changes. Agree? Okay, good. So now let us understand. I will start the slides now so that it's easier, and then we will discuss. Okay, so the three downlink reference signals. One is the CSIRS, then the DMRS, and another is PTRS. We're going to start with the DMRS. Okay? DMRS is the main reference signal that are embedded into the PDSCH so that they can do channel estimation. Okay, sorry. I think this is a wrong. So this is what we saw. The sequence generation is what we saw. Okay. Again, the serial table, as I said, depends on the slot number as well as the symbol number. We'll see these parameters in a minute. We'll come to this and how it's. Okay. So now the next question is, so now you have generated the sequence based on the slot number and the sequence number. You have some QPSK symbols. How do you put in the grid? Okay. There are two types of DMRS signals. One is called the type 1 DMRS, another is called the type 2 DMRS. Okay. So if you look at type 1 DMRS, type 1 DMRS is of density half. Okay. So what I mean by density half is every alternative resource element is a pilot symbol. Type 2 is one third density. One third density means every third resource element will be a pilot symbol, DMRS pilot symbol. Okay. So that is what they mean by type 1 and type 2. So this mapping, so it looks like a little bit complicated, but it's actually pretty straightforward. I'll tell you how to look at this mapping once. So R of n is a sequence that you have generated. Remember, R of n is a pilot sequence that you have generated. Okay. Forget about this WF and WT. These are the CDM types. Forget about them for now. Okay. Don't worry about it. We'll come to this later. Forget about beta. Beta is a power scaling parameter. Okay. So let's just focus on. So let's just focus on this part and this part. Okay, you forget about these three parameters for now. Okay, so alpha KL PU. Okay, remember this is something has K is the RE element number, L is the OFDM symbol number, P is the port number, mu is the subcarrier spacing. So we are just focusing only on one subcarrier spacing, so it's fine. We can forget about mu. So what you put in port P, kth symbol, kth resource element, and lth symbol is equal to R into 2n plus k dash. Yeah, R of n is a sequence that you have generated, remember. So R of 2n into R of 2n plus k dash. So k dash can be 0 or 1. Okay. And n is equal to 0, 1, 2, 3, 4, 5, 6, 7. Okay. What this is mapped to is given by k. So k dash and k are related by this particular equation. So you can see that what happens for configuration type 1, it is 4n, plus configuration type 2, it is 6n. Okay, I want you to see the examples, it will become very, very clear. Okay. Okay. We come and look at this very, very cleanly. I will show you the slides and we can do this. Okay. So remember there are two types, type 1 and type 2 DMRS types. Type 1 is half density and type 2 is 1/3 density. I'll show you examples in a minute. Okay. On top of this, there are other two things that are very, very important. This is for PDSCH. Okay. There are two types of PDSCH. One is called the type A PDSCH mapping and type 2 PDSCH mapping. Okay. So there are other names for this. Type A PDSCH mapping is called this, slot-based scheduling. Okay, this is called the slot-based scheduling, type A. Type B is called the mini slot based scheduling. Okay, these are informal names for it, but I'm just telling you. Okay, so what type A means is this. So this is our resource grid, the whole resource grid. Okay, you have 14 symbols and there are multiple resource elements. I mean, I just drew up to 35, but there are multiple resource elements. Okay, type A means whatever you tell, always the allocation for a particular user is always defined with respect to the starting of the slot, which is the 0th symbol. Okay, so everything is measured with respect to this line. You can see my cursor. There is a line in which it's relatively measured to. That's called type A. So LD is the duration between the first OFDM symbol of the slot and the last scheduled OFDM symbol of the slot. L is defined with, so essentially everything is defined with relative to this particular line. Okay. So if they tell, for example, if they tell you put you put the DMRs in the third symbol. The third symbol means 0, 1, 2, 3. That's how you should count. Okay, you should always start with this for type A. Type B, on the other hand, the counting always starts relative to the PDSEH allocation. Suppose this orange is the PDSEH allocation. This is what is allocated to the user. Then the counting always starts with respect to the starting of the PDSEH allocation. So it starts at this point. So when they say L is equal to 3 in the type B, it means 0. 0 starts here. 1, 2, 3. This will be third. You understood the difference between these two? So there are two types of PDSEH mappings. Okay, it's called the type A and type B. Type A means essentially the allocation and the counting is with respect to the start of the slot. Type B is with respect to always to the relative to the start of your PDSEH mapping. Is this clear?
Yes, sir.
Okay. So essentially the main reason for introduction of type B was preemptive scheduling. Okay. So that, I mean, essentially this is the notion of a mini slot. We'll come to this later. It all boils down to that particular thing, whereas type A was a more conventional LTE based kind of a thing where everything was defined in relative to the start of the slot. Okay, so don't confuse type A, type B with type 1, type 2. Type 1, type 2 are the densities of the DMRS. Type A and type B are the what do you say, time domain location. I mean, how you count the time domain locations for PDSEH. Okay. Okay. So I'm going to tell you more about the so we'll get back to the DMRS again. So there are two types of DMRS. One is called single symbol DMRS and the other is called double symbol DMRS. Okay. So this I'll explain you with my iPad. Just give me 1 minute. Okay. So single symbol DMRS means I'm just here putting type A, where I'm talking relative to the start of this slot. This is 0. Okay, 14 OPM symbols are there. Okay, so single symbol DMRS means essentially the DMRS, it may be in different location. I'm just giving an example where it's located in the second symbol, 0, 1, 2 symbol, but the DMRS is present only here. Okay, there's something called double symbol DMRS in which DMRS will be like this. Okay, so DMRS is there in the adjacent symbols. Okay, this is called the double symbol DMRS. Okay. So what is meant by double? Why do we require double symbol DMRS? Okay, what is the use of double symbol DMRS and what is the use of single symbol DMRS? Single symbol versus double symbol. Okay. Can anyone can you think about why do you want to use double symbol and why do you want to use single symbol?
The single channel, single symbol DMRS will estimate the channel, but double symbol will give the more accurate while estimating the channel.
Okay. So one thing, one thing is one advantage is it's more accurate channel measurement. Okay. So at this point, I'll also talk something about this. Okay, that's one point, one correct point. Okay. What about any other reason why there's a double symbol DMRS? Okay, so let me tell you one more reason, one more interesting reason. I mean, so with the double symbol DMRS, which are adjacent to each other, you can do frequency offset estimation. Okay, so one, as Pandey sir told, one is, of course, you can get better channel estimate. I'll again come back to this point in 1 minute. Okay, but more, I mean, another important thing that is possible by a double symbol DMRS is you can do frequency offset estimation. Okay, so remember when we did OFDM, when we did in the beginning of the when we started this course, one thing I told you was OFDM is very sensitive to sensitive to frequency offset. Yes, frequency offset should be corrected. The multiple, we saw some few ways of correcting the frequency offset. One is CP based correlation and finding out the frequency offset. That's one way of doing frequency offset correction. So other way of I mean, even when you all do all that, what will happen is there will be some residual frequency offset correction or Doppler. When specifically in high mobility, there's case of high Doppler. What you can do is you can use these two adjacent symbols to do frequency estimation. Okay. I will not go into the method. Maybe I will describe this in a homework problem or something so that you can play around with this a little bit. I will put some equations and send it to you. You can read that up. Okay. But saying that, this is one more, I mean, this is good to remember that double symbol DMRS will help you in that. Okay. In addition to this, there's one more important point is double symbol DMRS gives you more ports. Okay, we'll see that later. It gives you more ports. Okay. Double symbol DMRS gives you more ports. Okay. So just continuing on this argument. So this is the resource grid. Okay. So you have DMRS here, 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 here. Okay. Let's assume single symbol. Okay. Let me erase the other parts. Okay. So you have single symbol DMRS. Okay. So now where is your data? Your data is there all around. Every other thing. So in this green thing, every other resource element has data. Yes. Every other resource element, every other has data. Okay. So you have to now estimate the channel. So how do you estimate the channel? At this point, you know the channel. At this point, you know the channel. This point, you know the channel. This point, you know the channel. Okay. So when you have a channel,
sir, your cursor is not visible, sir.
Sir, is this okay now? 1 minute. It's being very slow. Is it okay? Can you see my cursor? I wrote something here.
So now I.
Sir, actually cursor is visible, but delay is happening.
Yeah, the delay. I don't know why the delay is happening. I mean, okay. So I'll speak a little bit slow today, so that there's some correlation between what I speak and what you see. Okay. So what I'm saying is, in these points you can estimate the channel. Yes, because the DMRS are there. These 4 things you can estimate the channel because DMRS are all there. And now what you should do, you should try to find out the channel on every other RE. Okay, because these are the only 4 pilots that are there in this whole grid, in this green grid. Okay, so how do you do this? In the frequency domain, what they do is they do linear interpolation. Essentially, they interpolate between these 2. Okay, these two. Okay, you can do the interpolation across the DMRS to get the frequency domain estimates. Okay. So what about time? Can you just hold on 1 minute? Let me just see if some problem is there. Just give me 1 minute. Okay, so it's very easy to interpolate. So remember, this is one, each of this is one OFDM symbol. Okay, so for this OFDM symbol, it's very easy to get the frequency response across the entire thing. But what do you do across the time? How do you find the channel across the time? So one assumption that you make is, so it depends on the speed of your mobile. If the speed of your mobile is very high, then the channel is going to change from one symbol to another symbol. So this is one symbol, this is the second symbol, third symbol, fourth symbol, fifth symbol, so on. Okay. If you're a static user, then most probably your channel, whatever channel you have estimated in this symbol, in the first wherever the DMRS is, the same thing can be used across all the other symbols. Okay, the same thing can be used across all symbols. But okay, but if you're high speed mobile, then what happens? The channel is going to change every symbol. Okay, the channel is going to change every symbol, and it's very difficult. So essentially, how do you use the older the channel estimate that you have obtained in symbol number 3 to the channel estimate you have to the symbol 14? Okay, it will change. So what they do is, this another type of DMRS is called as multiple locations of DMRS is also possible. So what I mean is, you can also introduce DMRS across another location. Okay, so because of this, what happens? Because of this, what happens? You can actually interpolate. So you will know the channel, exact channel one in you know the exact channel here in this symbol, in this whole symbol. Okay, you will also know the exact channel in this symbol. Fine. So what you can do, then you can interpolate easily. Then you do interpolation across the time domain also. Okay. So you are going to see double symbol DMRS. Double symbol DMRS means essentially the DMRS is adjacent.
Excuse me, sir. So second set of DMRS will come after a delay of certain OFDM symbols.
Yes.
But
yes.
before that, in between the OFDM symbol have come. So we will estimate it when we receive the DMRS of the second set. But before that, how we will get that OFDM signal at the receiver end?
Yeah, very good question, sir. So what if you have something like this double symbol DMRS, then you have to store the entire slot. You have to wait till the entire slot comes, till the second DMRS comes, and only then decode it.
Okay, yes, sir. Then only it's possible, sir. Very good.
Yeah. So essentially, that's why. So some people feel, some users, depending upon your implementation, some users feel that double symbol DMRS means you have to store a lot of data. Nah? You have to store 14 symbols of data. Okay. So that might be expensive in terms of implementation. It also increase latency. Whereas if it's single symbol if it is only one DMRS position, then what you can do is immediately after you get the third symbol, 0, 1, 2, second symbol, you can start decoding everything. You can only have to only store for 3 symbols.
Sir, alternatively, we can't do like that. Every OFDM symbol we can give some resource element for the DMRS, no, and then
it doesn't allow. So the spec doesn't allow.
The spec doesn't allow. Okay.
Doesn't allow that.
What's the reason behind this, sir?
Sir, because DMRS is also overhead. Whenever you transmit DMRS, it's a waste of resources. I mean, you're not actually transferring data. Okay.
Okay, sir. Yes.
So mainly you use this kind of I mean, DMRs at different locations. Mainly you use if there's high mobility, because channel changes very fast. On the other hand, if you are a low mobility user or a static user, then one simple DMRS will be fine. One DMRS location will be fine, because you can assume that the channel is more or less constant. Okay. So in general, what happens is, until unless your estimation algorithms actually do good interpolation, if there's only one simple DMRS, then the last OFDM symbol will generally have higher EVM, higher error rate. Okay, because I mean, even whatever you do, there will be some slight change in the channel. I mean, over some duration. Okay, so you have to have very efficient ways of understanding how do you interpolate the channel across time. Okay, so effectively, what it happens is channel estimation is one of the major blocks in any of these implementations. One is timing recovery, the SSB recovery, and other things. And the other thing is the channel estimation. Okay, so both of them are extremely complicated blocks. Fine. Any questions?
No, sir.
Oh. Okay, so you understood the difference. There are 3-4 differences. One is single symbol DMRS, other is double symbol DMRS, and third thing is DMRS has different locations. There are three different things. Okay, double symbol DMRS is not. DMRS has different locations. The double symbol DMRS always happens adjacently. Okay, single symbol DMRS you understood. Double symbol DMRS they occur in the adjacent symbols, and DMRS at different locations means they occur at different locations. Okay. So as I said before, single symbol DMRS supports a maximum of 6 ports. Double symbol DMRS supports 12 ports.
Sir, 1 minute, sir. That DMRS at the different symbol can be of the single symbol or double symbol.
It can be both.
It can be both. Yes.
It can be both. I'll show you examples of that. Okay. So you should, I mean, one of the points I should now count is, remember, DMRS is the one which we are going to use, one of the reference signals pilots that we are going to use to estimate our MIMO channel. Okay, so if you use single symbol, you can use a maximum of 6 ports for that user. Okay, 6 ports means effectively maximum of 6 layers can be used. Okay, you understood a port definition. Huh? If on the other hand, if you use double symbol DMRS, you can support 12 ports. It will become very clear why that is the case. Okay. So it says, so if this table in 38211 says, if you are using single symbol DMRS, the port numbers go from, see, it's configuration type 1 or configuration type 2. Type 1 and type 2 we saw now, just now, type 1 and type 2. What is type 1? Type 1 is density half, type 2 is density 1/3. Okay, so type 1 can support only 4 ports, type 2 can support 6 ports. Okay, the reason they did that was because type 2 is 1/3 density, so the overhead is less, so they try to support more ports with that. On the other hand, if you use double symbol DMRS, with type 1 itself you can support 8 ports, and type 2 you can support 12 ports. Is this clear? Did you understand this? Forget about this L dash. L dash is 0, 1 means it's there for 2 symbols. L dash 0 means it's there only for single symbol. That's what it means. Okay.
This is it is okay with this that table, but how you can visualize this?
I'm going to show you more a lot of examples now. Wait. Maybe we'll just go to the examples and come back and do the other class. First, let's do. Forget about these parameters. I will tell you what these parameters are later. Don't worry about that. Okay. So let's just look at the pictures here and then understand and come back to this, what those means, additional positions, LDs and other things mean. Okay. So this is an example of a single port DMRS. Okay. Single port DMRS type 1. Okay. Type 1 means what? Density half. So every other alternative RE, you have a, what do you say, DMRS. Is this clear? Now let us do. So with single port, how do you do? Sorry, single symbol type 1 single symbol. How do you do 2 ports? Okay. There are 2 ways of doing this. Okay. So one way of doing this is this. They use CDM. So essentially, this is port 0, port 1000, and this is port 1001. Okay, single symbol DMR, single symbol DMRS type 1. Okay, so this is where you send your DMRS positions. So here, what you do is you multiply this element, whatever you see here, with -1 and transmit in the port other port. This one you keep the same. This one you multiply with -1. This one you multiply by -1, -1. Okay. Now what they do is they consider these two and these two as a CDM group, one CDM group. We saw the CDM now. So if you think about it, the channel is constant across these two, and the channel is constant across these two, you'll be able to decode this because this is orthogonal to this. Okay? It's 2 port. What I will do is in I actually showed that here. Here, this is what happens. We already saw this. I mean, the assumption is that the channel is constant across these two frequencies. Okay, so you get first equation, you get H1P1 plus H1P1 plus minus H2P2. Sorry. So P1H1 plus P1H2, and similarly P2H1 minus P2H2. You can solve for H1 and H2. Okay, so the assumption is that the channel is remaining constant across these 2 subcarriers. Okay, so in this case, when I say 2 subcarriers, two DMRs, okay, it means that these 3 locations, you assume your channel is constant. Okay, so these 2 locations and these 2 locations, your channel is constant. Okay, so you understood how you send it across 2 ports. So what I'm going to do is I'm going to stop now. There's too much lag in what I'm talking and what I'm showing here for some reason. Okay, let me fix this up. Next class, we can continue with this. I will show you more examples. Also, I have made a lot of examples on showing multiple single port, dual port, and other things. Let me add more examples to this, and we'll see. I'll try to fix up this problem of lag. I don't know what is the issue that's happening, why that is happening. It will become easier for us also, for me also to teach. Okay, so we'll stop at this point in the next class. So I will share the slides. What you do is you please look at the slides. Meanwhile, in the next class, we'll try to finish up this DMRS, and we'll also look at more technical details on the resource, the information elements and other things in the next class. Okay.
Okay, sir.
Okay. So one question is, next Monday, this Monday, can I take one class? I mean, if everyone is fine, I will take a class on Monday for half an hour so that I can compensate for what we have lost today.
Monday we have got our own some sessions, sir.
Okay, fine. Then no need. We'll come. I'm just going to stop recording. I was going to ask something.